Look up at the night sky tonight and take a long look at the moon. It seems permanent, reassuring, fixed. But around 4.5 billion years ago, the moon did not exist. The Earth was alone, younger, hotter, spinning nearly 3 times faster than it does today. And somewhere in the darkness, another world was on a collision course with ours. What happened next was the most violent event in our planet's history, and it gave us everything. This is the early Earth, a largely molten world, still being assembled by constant bombardment from the debris left over from the sun's formation. There were no oceans yet, no continents, no life, just a churning ball of rock and metal, slowly cooling at its surface and violently hot inside. At the same time, not far away in orbital terms, another rocky planet was forming. Scientists have named it Theia, after the Titan goddess in Greek mythology who was the mother of the moon. Theia was roughly the size of Mars, about half the diameter of Earth, perhaps 1/10 of its mass. Not small. For millions of years, Theia moved in an orbit not entirely unlike Earth's, close enough and gravitationally influenced enough that eventually those two orbits could not stay separate forever. The collision, when it came, was not head-on. Theia struck at an oblique angle, a glancing blow, like a billiard ball striking another from the side. This detail matters enormously. At the moment of impact, the speed was somewhere in the range of tens of thousands of kilometers per hour. The energy release in that fraction of a second was beyond any scale we comfortably understand. Theia did not bounce. It did not simply crater the Earth. It merged with it, and in doing so, blasted an enormous cloud of vaporized and molten rock out into space. In the hours and days that followed, a large fraction of Theia's material, along with rock vaporized from Earth's outer layers, was flung into orbit around our wounded, reshaped planet. The iron cores of both bodies, being much denser, mostly sank inward and merged. This is partly why Earth has such a large iron core. It contains some of Theia's iron as well as its own. What remained in orbit was an enormous ring of debris, rock, vapor, dust, and heat, swirling around the Earth like a thick, glowing disk. Now, gravity did what it always does. It pulled things together. Within perhaps a few hundred to a few thousand years, an eye blink in geological time, the debris in that orbiting ring began to clump. Small fragments collided and stuck, growing larger, attracting more material. This process is called accretion. The same process that built the planets themselves, now happening again, in miniature, right next to the Earth. Relatively quickly, a single dominant body emerged from the ring, a new world, still molten, still glowing, orbiting very close to Earth, the moon in its earliest form. At this point, the moon was much closer to Earth, perhaps 15 to 20 times closer than it is today. At that distance, it would have appeared enormous in the sky, roughly 15 times wider than it appears now. Earth's tides would have been hundreds of meters high. The planet was spinning much faster, a day lasting perhaps only 6 hours. Gradually, over hundreds of millions of years, the moon's surface cooled. Its magma ocean solidified into the gray highlands we see today. The deep craters pockmarking its face were formed during the late heavy bombardment, a period when leftover debris from the solar system's formation rained down on every rocky body in the inner solar system. Here is something that might surprise you. Right now, as you watch this video, the moon is moving away from Earth. Not dramatically, not visibly, but measurably. The moon is retreating from Earth at a rate of approximately 3.8 centimeters per year, roughly the rate at which your fingernails grow. This happens because of tidal forces. As the moon's gravity pulls on Earth's oceans, it creates tidal bulges. But Earth is rotating faster than the moon orbits, so these tidal bulges are always slightly ahead of the moon's position. That slight offset creates a gravitational tug that pulls the moon forward in its orbit, and physics dictates that this gives the moon more orbital energy, pushing it gradually outward. We know this with extraordinary precision because of laser retroreflectors left on the lunar surface by Apollo astronauts. Scientists fire a laser at the moon and time how long the pulse takes to return. That measurement is accurate to within millimeters, and it has confirmed year after year that the moon is drifting outward. As the moon moves away, its grip on Earth's rotation slowly weakens. Our days are getting longer by about 1.4 milliseconds every century. The moon is not merely a pretty light in the night sky. It is one reason life on Earth has been stable enough to persist for billions of years. The moon's gravitational influence stabilizes the tilt of Earth's rotational axis. Without it, that tilt could wobble dramatically over time, causing extreme and chaotic swings in climate. Life, as complex as it is, may never have had the chance to take hold. The tides driven by the moon may also have played a role in the origin of life itself, cycling coastal zones between wet and dry, concentrating organic chemicals in tide pools, driving the chemistry that could have assembled the first biological molecules. And that is the strangeness of it all. A catastrophic, almost random collision, a wandering planet that happened to be in the wrong orbit at the wrong time, produced the very companion that helped make Earth habitable. The moon was not placed there for us, it was born from destruction. Every time you see the moon, you are looking at the scar of a collision that should have been the end of everything, and was instead the beginning.